And I'm going to slide an object from this direction. Let's clean it a little bit better. Here is that roller coaster. This is a circle, and then it goes up again. So let the circle have a radius r. This point be A. I release it with 0 speed. I assume that there is no friction for now. This point be B. And I define here y equals 0, or what is even more important, I define that u equals 0. And this is the direction, positive direction of y. At A, the object has no velocity, no speed. At B, of course, it does. It has converted some potential energy to kinetic energy. At this point, C, it had reached a maximum velocity that it can ever have, because all the potential energy has been converted to kinetic energy. And at this point, D, if it ever reaches that point, that will be the velocity, say. Okay, I start off, point A is at a distance h above this level. And so I apply now the conservation of mechanical energy. So I know that U at A plus the kinetic energy at A, which is 0, must be U at B plus kinetic energy at B, must be U at C plus kinetic energy at C, must be U at D plus kinetic energy at D. If there is no friction, if there are no other forces, only gravity. So we lose no energy goes lost in terms of friction. We know that this high difference is 2r. And so now I can write this in general terms of y. Point, say, take this point B, think of that being at a location y above the 0 line. Then I can write down now that UA, which is mgh, that was a given when I started, that was all the energy I had, that was my total mechanical energy. If I call this U0, which is free choice I have, equals U of B, which is now mgy plus 1/2 m v squared at that position y. This should hold, what you see there should hold for every point that I have here. It should hold for A, for B, for C, for D, for any point. I lose my m. And so you find here that, let me summarize it, that v squared equals 2g times h minus y. So this should hold for all these points. Therefore, it should also hold for point D. However, at point D, there is something very important. There is a requirement. There is a requirement that there is a centripetal acceleration, which is in this direction, a centripetal. And that centripetal acceleration is a must for this object to reach that point D. And that centripetal acceleration, as we remember from when we played with the bucket of water, that is v squared divided by r. And this must be larger or equal to the gravitational acceleration g. If it is not larger, the bucket of water would not have made it to that point D. So this is my second equation that I'm going to use. So look very carefully. So v squared must be larger or equal than gr. So I have here v squared, which is 2g times h minus y, but y for that point D is 2r. So I put in a 2r, must be larger or equal to gr. I lose my g, so 2h minus 4r must be larger or equal to r, so h must be larger or equal to 2.5r. This is a classic result that almost every person who has taken physics will remember. It is by no means intuitive. It means that if I have a ball here, and I will show you that shortly, and I let the ball go into this roller coaster that it will not make this point unless I release it from a point that is at least 2.5 times the radius of this circle above the 0 level. If I do it any lower, it will not make it. So think about this. That is something that you could not have just easily predicted. It's a very strong result, but it is not something that you say intuitively, oh yes, of course. It follows immediately from the conservation of mechanical energy. So if I release it, that 2.5 radius point, by the way, is somewhere here. So if I release this object way below that, it will not make this point. Let's do that. You see it didn't make it. I go a little higher, didn't make it. I go a little higher, didn't make it. Go a little higher, still didn't make it. Now I go to the 2.5 mark, and now it makes it. 2.5 times the radius. Conservation of mechanical energy tells you that that is the minimum it takes to just go through that point. Of course, if there were no loss of energy at all, if there were no mechanical energy lost, that means if there were no friction, then if I were to release it at this point, it would have to make it back to this point again with 0 kinetic energy. But that's not the case. There's always a little bit of friction with the track for one thing, and also of course with air. So if I release it all the way here, you will not expect that it will bounce up all the way to here. It will probably stop somewhere there. It may not even make it to the end. We can try that. Oh, it made it somewhere to here. It's a little lower than that level, because there is some friction that's unavoidable.